In this video, we're going to review how array access happens in x86 assembly. Let's start with a simple case of one-dimensional arrays. Suppose we have a one-dimensional array A of 10 ints, and suppose we've initialized our array to contain the numbers 0 through 9. In C, we declare this as follows. Conceptually, then, our array looks like this. A is actually just a pointer to the first element of the array. We can select the ith element of the array relative to that pointer using standard C syntax for an array element, AI. Alternatively, we can use C pointer arithmetic to select the ith element. It's the one pointed to by A plus I. For example, element A2 is the one pointed to by pointer A plus 2. We can select A2 by dereferencing the pointer A plus 2. Here's the first fact to keep in mind about arrays. Fact 1. Array elements are always allocated in order in consecutive memory locations. Thus, in memory we actually have a structure like this. Again, A is just a pointer to the first element in memory, and A plus I is a pointer to the ith element. That's the model of what happens at the level of C. But what about at the x86 assembler level? First, recall that the x86 memory is byte addressable, and an int occupies 4 bytes. Therefore, our 10 int array actually requires 40 bytes in memory. From fact 1, we know that they'll be allocated consecutively. To make our picture appropriate to the machine level view, we replace our C pointers with x86 memory addresses. A is still the address to the first element in the array, but successive array elements are 4 addresses apart, since each int requires 4 bytes of storage. Each array element actually is stored across 4 bytes in Little Endian fashion, but we won't bother to show that here. Now let's talk about accessing the ith element of the array. We have the address A of the start, or base, of the array, and we also have the index I of the element we'd like to access. Because of fact 1, we know that there are I elements preceding AI in the array, and each of them occupies 4 bytes. It's easy then to see that the address of the ith element is A plus 4I. Of course, had this been an array of some element type other than int, we would have replaced the multiplier 4 by the size in bytes of the element type. The implication of all this is that array accessing is very fast, since you can access directly any element of the array just by computing its address in memory. Now let's consider a two-dimensional array. Suppose we declare a 2D array of ints in C as follows. Array B has 5 rows and 4 columns, 20 elements altogether. And since an element is an int, that requires 4 times 20 or 80 bytes of storage. Here's a second fact you'll need to know. Fact 2. Multi-dimensional arrays in C are stored in row major order. Row major order means that the elements of the array are stored row by row. For example, the 20 elements from our 5 by 4 array would be stored in the memory consecutively as follows. In general, a two-dimensional array A with R rows and C columns would look like this. Now suppose we want to access an arbitrary element in A, say in row I and column J. Because 2D arrays are stored in row major order and rows are numbered starting with 0, if we're in the ith row, there are I rows above us that would be stored before our row. Each of those I rows contains a number of elements equal to the total number of columns C. That means that there are a total of I times C elements in those I rows above us. Each of those elements requires a number of bytes appropriate for the element type. Let's call that K. For example, for an int array, K equals 4, since an int occupies 4 bytes. Therefore, For any element in the ith row, there are I times C times K bytes in the I rows above us that will be stored before our row. Additionally, since Aij is in the jth column, there are also j elements in the current row to the left of our position. Those will be stored before Aij in memory. That means an additional j times k bytes above us in memory. Now let's put it all together. Since the elements of the array are stored in consecutive bytes beginning at address A, and since the elements are stored in row major order, an arbitrary array element Aij will be stored at address A plus I times C times K plus J times K. For example, take our 5x4 array B. Suppose we want to compute the address of element B42. For this example, I equals 4, J equals 2. C equals 4 since there are 4 columns in array B, and K equals 4 since an int occupies 4 bytes of storage. Finally, B is the address of the start of the array in memory. Filling these values into our formula means that the address of B42 is B plus 4 times 4 times 4 plus 2 times 4, which equals B plus 72. That is, the int at array location B42 occupies the 4 bytes of memory starting at address B plus 72. The implication is that we can access an element in a two-dimensional array directly simply by computing its address in memory.